Hello to everybody. Welcome to today's webinar, a partner webinar of Autodesk and IDEA StatiCa. I hope you can all hear us. We are using GoToWebinar. If anything goes wrong, it's on the ribbon on the right. You can either adjust your audio settings or type in any questions you have. We'll be covering them during the whole webinar as well as the end. Allow me to introduce the speakers. It gives me great pleasure to announce Udo Hedicke, Product Manager, Structural Steel at Autodesk, and my colleague, Product Engineer Adam, myself, Juraj, also from IDEA StatiCa. We prepared content for today in two regards. One is an overview of the connected workflows at the BIM table, and then we'll pick two examples from them, and we'll take a closer look how to do code checking, structural design of complex steel joints. So first one will be from Revit, second one will be from Advanced Steel. We'll be switching mics. We will cover all your questions after the end. Kindly spend 30 seconds on filling out the short survey. We will send a recording of that webinar as well. And for more information, do not hesitate to contact our website. We have a dedicated section on the partnership with Autodesk as well. Let's jump right into the content. We will kick it off with a presentation of Udo, who will elaborate on the connected workflows today, how it all works, and how you can benefit from that.
Thanks, Juraj, and good morning as well from my side. Yeah, as you said, I'm Udo, and I'm product manager here at Autodesk for structural steel. So basically here at Autodesk, we are on the path of connected BIM. I mean, we all know that BIM allows for earlier design, insight, and decision making, allowing changes to be made when it's less costly. Because BIM automates the production and coordination of much of the design and construction documentation needed on a project, structural professionals like you can spend more time on design and modeling, like finding the best solution for a challenging steel connection situation, while the need less time on tedious, resource-intensive tasks. Connected BIM. Here is BIM plus the power of the cloud. It's a cloud-enabled, intelligent, model-based process that unites the design, build, and operate segments. We are doing this connected BIM because we are already seeing some incredible changes in the structural industry and a number of trends that are tightly connected to how teams are using technology. Some of these include owners realizing the benefits of BIM and the associated project savings, leading to more BIM mandates and the advancement of new standards supporting BIM maturity, national BIM standards, and LOD requirements across the world. As optimized designs include greater detail, there is an explosion of data produced by BIM projects with higher fidelity at a greater frequency than that of 2D information, especially with increased computational power. Technology is removing barriers to collaborate across distances. Teams are assembled across different offices and geos representing larger talent pools. These trends are causing engineers to extend their services downstream and fabricators and installers to extend their services upstream. Teams are relying more and more on data to communicate. Our Autodesk portfolio of BIM technology supports end-to-end workflows across the building disciplines from the project's conception to completion. With our tools, you can begin BIM workflows even at the conceptual stage of structural design. Both conceptual design and analysis tools are built right into our BIM authoring applications. In addition, our solutions are interoperable and help you move from one phase of the structural delivery process to the next, so that you can seamlessly collaborate from your structural design through the construction phase of your project. Next, I want to talk quickly on a customer project where connected BIM was key for project success. The Louvre Abu Dhabi, which opens pretty soon, will be a unique museum where artwork from around the world will be showcased at the museum, with particular focus placed upon bridging the gap between Eastern and Western art. Its approximately size is 260,000 square foot. Also, this is another iconic project where clients used Autodesk solutions like Revit and Advance Steel to increase productivity on a complicated project. The Vienna-based engineering office Wagner Biro used Advance Steel to detail the steel on the museum's complex dome, which was designed with 7,384 unique star-shaped features. Advanced Steel helped them to work with the engineer from the very beginning of the design process, so they created a 3D model in an elevated state in order to coordinate with them. While there are many benefits of disconnected BIM, we will focus today with IDEA StatiCa on the analyzing and verification of structural steel connections. During this stage, structural engineers and detailers have access to tools that allow them to perform, for example, a seamless connection between design and analyze. So let's give Adam some time now to highlight the great workflow that exists already between IDEA StatiCa and our Autodesk solutions.
Okay. All right. I hope you can hear me. And greetings once again. Welcome to our session. And I'll be showing you two examples, as Uri said before. I will start right away with the Revit link example about the export of one joint of this model that I have in Revit. This is a steel structure, a steel hull, and I'll be exporting one of those joints here into IDEA StatiCa connection, and we will calculate that joint and check it according to codes. So since you install IDEA StatiCa, it integrates into your softwares. We support many of them now, for example, Revit, Advance Steel, and so on. You can check that on our webpage, and let's do the workflow right now. So here on the bar on the ribbon, you just pick the IDEA StatiCa command, and let me see, there is something wrong with that. I'll try to fix that. Okay. Seems that it doesn't want to go now. Okay, I will restart the application, and in the meantime, I will show you the link with Advanced Steel that I wanted to show you before. So as a second example. So let's start with Advanced Steel now. And this is a steel hull model in Advanced Design as a CAD software. So let's export that to IDEA StatiCa. For that, we use a command, which is a command concheck. And this we type in, and it asks us to select the node of the joint and select members of the joint that we have 4 here. And this truss roof joint, and we select the items like plates, bolts, and welds. And now this joint is being exported to IDEA StatiCa, which opens immediately. And here we can see the joint imported. Just start the Revit here in the meantime. Okay, so this is how it looks now in IDEA. We have the software set so that you work in, let's say, 3 steps: geometry, load effects, and design here in the menu. And if you go through those 3 steps, you are ready to calculate the joint. And since we imported the geometry from Advanced Steel, the geometry is all set here. So we have all those 4 members here imported, so there's nothing to do for us. If I jump right away into design, where we design the connecting operations like bolts, plates, welds, and so on, those are also imported from Advanced Steel and listed here. So this is just to take a look. And then we go to load effects, which are not imported from Advanced Steel because it's just a CAD software. And we can add them here manually. Just write the numbers, the figures, and check it in the 3D screen. So we can just fill the table with.
Adam, sorry
yes.
for interrupting. On my side, I still see the Advanced Steel.
Oh, really?
Yeah. Yeah.
Okay.
Maybe you have paused your screen sharing?
Not really.
You can just try to stop the sharing and launch it again. It's probably
okay,
a frozen window.
Okay.
Okay, now I see.
I'll try that.
Yeah. Now I see.
Yeah, is it
Now
better?
it works. Now it works. Okay, so yeah.
Okay. Okay. Good. Well, we have some technical issues, obviously, today. So let's go again to geometry. As I was talking about, those are the 3 steps here in the menu on the left side. The geometry, where we can see the 4 members listed, the 4 beams, and the design menu, where we can see all the operations listed, imported from Advanced Steel. And then we go to load effects, and we can input manually the forces that we have calculated in some structure calculation software or elsewhere, like this, or just fill the table, or we can import them and copy and paste them from an Excel sheet, which I have prepared. This is an Excel sheet with some forces, internal forces values, and I'm going to import them and copy them into IDEA StatiCa. So you do this by clicking import and just paste them like this. Click OK, and they are set on the members. As we can see, you can check that always in the 3D window where they are placed, just to be sure. Okay, so this is it. And the last step is just to click the calculate. And I'll open here the project in Revit. And this is now being calculated and analyzed. This is a iterative process, calculating step by step, rising the loads, and usually takes about a minute or half a minute for such joints. And now what we can see is the first result display, an overall check, or how we call it, the traffic lights display. Here the joint is colored in 4 colors: gray, green, orange, and some parts are red, in the case that some parts don't pass the code checks, which didn't happen here. And those colors mean that the gray means that the utilization of such members or plates or bolts is up to 60% of its capacity. Green means it's 60 to 95%. Orange is 95 to 100, so almost on the limit of its capacity, and what is over 100 is then colored in red and didn't pass the check, and is also mentioned here in the tabs on the left side of the screen. So this is overall check, very quick overview what's happening there. And then we can go through the other result displays, like strain checks, to see where strain occurs in the joint. We can display equivalent stress, how it is distributed along the joint. We can turn on the mesh display to see how it is meshed. You can check plastic strain on the members. There is just some small one next to the bolts here, and we can turn on the bolt forces, and we can also directly click on the bolt force here, which shows us the tab, or we can go there just here by clicking those tabs here and browse the results each by one. For example, for this bolt that we highlighted by clicking here, you can also open the equations according to the code, what is behind those figures here in the tab. So it's all listed here. The same for welds and plates and so on. So this is about the results, and now I'll jump back to Revit, and I'll now export the joint from Revit to IDEA StatiCa. This is a wizard for the link from CEA programs, or the structural programs linked to IDEA. So it asks us to save the project somewhere. So we do that, and here we can, in the next window, we can set the support to any of those members that we are importing, and we can just do it later on in the software. So we can just go right in there to see what we actually imported, and this is now looking like this. So basically we imported, if you go to geometry, we imported the geometry, we imported the column and 2 beams with their cross sections and geometrical settings. Okay, and since Revit is also having the information about internal forces, and we imported also internal forces. So we've imported actually 2 combinations here, just in one step. You can import as many as you like, or as many as you have there. So this is for the load effects. There's nothing more to do. So we go into the 3rd step, and that is design. And here we must add some operations to actually model the connection of connections of those 2 beams to the column. And for that, we have a library or a list of operations that can be edited also, and we just pick one, and I will start with this beam. So for that, I will use the end plate operation. Okay, I will start with some bolt assembly that I like, for example, this one, and we can change that also during the workflow here. And for each operation, we can have a different bolt assembly as well. So that's just something for beginning. Okay, so we have added an end plate, and I will now modify a little bit its parameters. Like I will add some more steel here, like 10 millimeters. So now there's enough just below the weld, and I will move the bolt a little bit lower. Okay, so it's not so close to the edge. Okay, this is looking good. Can leave it like this, and we can add another operation to connect the second beam to the column. For this one, I will choose a cleat operation. So I will now take the member 700, and I will connect its web, and I will connect it to the column, which is the member 618. Okay, and the last thing is that I have to choose the profile that I will connect this member with. So I will use an angle, and I will pick from our library of cross sections, for example, this one, 50 by 5. Okay, so now it's looking like this. There's one side, and I would like to have it on both sides. So I will just pick here both. And so it's on both sides now. Okay, and I'll modify it a little bit. I will set its length to have it shorter, and I will also move the bolts a bit to the outside, and also a little bit to the edges, upside and downside. Okay. Oh, this is looking fine. This is how I like it. So I just go to check and calculate this. And now both of those combinations that I just imported from Revit is being calculated. And now the software is showing us the extreme of those two combinations. So it checks both of them step by step, and this is the result. This is the worst scenario, so we're always on the safe side, and this is now telling us that we passed the checks, and with the utilization of the capacity, we're about 50–60%. So what we can do now, and that is one of the advantages of our software, that we can easily optimize and recalculate in just half a minute the connection. So we can go just back to design, change parameters here, and calculate it again. So let's say I want to save some material here. I will use, instead of 10 millimeter thick end plate, I will have 5 millimeter or 6 millimeters maybe. And I will use different bolts, smaller ones, M12. Okay. So I save something here, and I'll do the same for the cleat. Also, I will change the angle cross-section, have smaller one, thinner one, like this. And I will also change the length of that. It's 100 maybe just, and I'll also change the bolt size like this. Okay. And let's see if this will be enough, since we changed that. And this is the way how you can optimize and how you can play and try different setups. Okay, so this is fine. We still passed the checks, and we're pretty nice, close to the limit, which is still okay. So we're having the joint also economically designed, not only safe. Okay, and you can play like this also with the geometry, with the angles of the beams like this. I can just put some angle here and recalculate that, or this one maybe like this, and just calculate this again. So this is very free to change anything in the setup. And the last thing is the report. And if you want to present your results, you go to the report and print it out on the paper or to PDF with this command, or you can save it to editable document that you can edit in your word processor, and it's all open for you. So here we list all the connection items, plates, pictures, all the results, all the checks, and so on. And you can edit this report also here, add other things that you like there or not, turn on some features and turn off some. Okay, I think that's it.
All right.
For the examples, and we can move to questions.
All right. Adam, can you please explain again what the colors represent in terms of usability, the traffic light display?
Sure. Okay, I'll go back to here. So this is calculated project, and here we can see the colors. Those are gray, green, orange, and what we are missing here is red, because we passed the checks here, so there is no red. The red is there only if we didn't pass. And the color is that the gray, what is colored in gray, is used up to 60% of its capacity. What is in green color is used 60 to 95% of its capacity, like those end plates here. What is colored in orange is used from 95 to 100 capacity, like this weld here. This is used for 98%. Okay, and this is according, of course, to the codes. So with all the safety factors and so on. So this is just telling you, okay, you passed the check and the capacity is close to the limit, but still on the safe side and all okay.
All right, thank you, Adam. The next questions, I will merge them. Possibilities of calculating stiffness and displaying them, stiffness diagram.
Okay, we have that. If you go here to project items, we have actually 4 types of analysis. What you've seen is a stress strain analysis, shows you the code checks. Then we have stiffness analysis, where you can just switch to this, and it calculates you the rotational stiffness of the member in a joint or the joint, and it creates you the stiffness curve of that and tells you the class of the joint, if it's pinned or rigid or semi-rigid, and you get the exact numbers as well.
All right. Is there any check about bolt distances from edges, so from ends of plates? Does the software tell us if we are designing it wrongly?
Yes, there is. It is by default, it won't let you calculate by the mean of the, let's say, mesh or the mathematical calculation. It won't let you calculate if you have the bolts, let's say, outside the plates, But there also is possibility to turn on we call it detailing, and this performs the check of bolt position. So tells you according to the codes if your bolts are not too close to the edge. So you can turn this on.
Very well. The next question is there design functionality or just code checking for the connection you put in? Just to make sure that I understand that correctly, this is about optimization. So maybe I can answer it right away. We can create any connection in the application in IDEA StatiCa. We can import any connection from Revit, Advance Steel, and other applications for the application to automatically generate the design. We have templates to speed up the process. And the optimization is, put it simple, trial and error. You adjust, you recalculate. This is an interesting idea for the future to define optimization patterns. But as of now, it works as such application to check what you see. All right. And I have 2 or 3 questions about the actually the link with Revit, what we get out, because from Revit theoretically we can get also the detailed connection, right? Because Revit is an application when it all merges, and if we upload the structural model combined with the detailed connections, as of now we export the structural model, but we will be able to export the detailed connection as well in the future. That's what we are working on with our colleagues from Autodesk. That's what our partnership is about, that we are improving the workflows, and we will be making this even better in the future. Very well. Yes, we got the question about the design optimization right. Very well. All right. We've covered all the questions. If we missed something, we will get back to you via email. Last thing is allow me to invite you for our next webinar we're doing. Let me share that quickly with you. We do regular online sessions. The next one, October 4th, we call it Connection Wednesday. It's every 2 weeks. It's a live online session focused on best practices in steel connection design. We usually demonstrate a complex customer project from around the world and some interesting question we get from our customers. We show how we model it. We discuss the approaches. It's usually 30 minutes. Refreshing. It runs twice during the day, so if you have time next Wednesday, feel free to join us. And for more webinars, everything is at our website. If you have not requested a trial yet, you can do so right away, and we will be looking forward to your questions and remarks. Very well. Okay, thank you very much for participating, and have a good day. Bye-bye.